about Unit 2.6, the general gas law. I'm skipping 2.5 because it's going to be easier for you to deal with 2.6 first. We'll do 2.5 after. So the general gas law basically takes all your simple gas laws that I have listed here and takes them and puts them into one big equation. So since we know that P times V always remains constant, P over T gives us a constant relationship. V over T, same thing. V over N, again the same story. And P over N, again the same thing. So since all of these ratios or relationships remain constant, if we put them all in relationship to each other, we obtain something like this. So pressure times volume over number of moles times temperature, still in Kelvin, will remain constant. So this whole relationship again is a constant ratio. And again, we can therefore assume that pressure times volume over moles times temperature will give us the same ratio again. So if we multiply one of these items by a certain factor, the other items will be affected accordingly. So this is what we call your general gas law, and that's when we're going to start playing with different variables at the same time. So we'll be modifying more than one aspect in this case. We might be playing with all four at the same time. So here are a couple of examples. So at SATP, 0.150 moles. So let me write down my variables, what I have, the information I have. I really suggest in problems like this that you do write down your information because there is a lot to deal with. So N1, is equal to 0.150 mole. A water vapor occupies a volume, so V1 is 55 milliliters. Now in this case, you have to put your volume in liters. So this becomes 0.0550 liters. Do not drop the zero because you have to take your significant figures into consideration. So if I had 55.0 milliliters, I have 0.0550 liter. Since this is at SATP, that means that my pressure, I can assume, is 101.3 kilopascal. Okay, so that's still my P1. And my T1 will be 25 degrees Celsius, which is 298 Kelvin. Okay. Now I'm going to list my other set of variables next to it. So N2. Let's keep reading. What is the new temperature? Okay, so temperature, T2, we don't know what it is. In degrees Celsius, if 0.030 mole of water vapor is removed, so now I don't have this amount anymore, I have 0.0550, here, I have 0.150 mole minus this amount, which gives me 0.12 mole. So 0.15 minus 0.03 gives me 0.12. Is removed while increasing the pressure. So the pressure now goes, P2, to 115.0 kilopascal. And decreasing the volume to 40. So V2 is equal to 40.0 ml. Which means I have to convert this into liters, 0.0400 liter. Now, I will replace in my equation, so let me just extend my page. Okay, so I have the following. Let me take another color. I'll write in red. So if I replace in my equation P1 V1 over blah, 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 so I get 101.3 times 0.0550 over N, which is 0.150 times 298 is equal to 115.0 times 0.0400 over N, which is 0.12 times T2. So I will get a T2 of 307.0 547. I have more decimals, but I don't need them. Now, this is in Kelvin, obviously. Now, first of all, I will verify my significant figures. So I have 4, 3, 3, 3, 4, 3, and 3. So the smallest is 3. So it should be 308 Kelvin. Now they want this in degrees Celsius, so I will minus 273, which gives me 35 degrees Celsius as a final answer. There you go, that's your example number 1. Moving on to example number 2. This one is a little particular. There's 2 ways of doing it. I will do it what I find is the simplest way, but some of you may not like it, so I'll give you an alternative after. So what will be the new pressure of a gas if we double the number of particles of gas and triple its temperature while keeping the volume fixed? So now they're not giving you any information. You have to either start replacing with numbers, which becomes a little complicated or longer, or what I personally prefer is to do it this way. So I start with my original equation. So P1 V1 equals, N1 T1 is equal to. What will be the new pressure? So I'm looking for P2 of the gas. If we double the number of particles of gas, so we have 2 times N1 because we doubled the particles, triple the temperature. So I have 3 times the value of T1 while keeping the volume fixed, so V1 remains the same. So now we'll simplify using another color. So my V1s remain the same, so I can cancel them out. My T1s cancel out. My N1s cancel out. So what am I really left with? I'm left with P1 on this side is equal to P2 over 2 times 3, which is 6, or if I rearrange, 6 times P1 is equal to P2. So my pressure changed by a volume of 6, it got multiplied by 6, right? So it's 6 times bigger. So P2 is 6 times bigger than P1. So there you go. Now, if you wanted, what you could do is assign a value to P1. Let's say you say it's 100 kilopascal. You'll look for P2, obviously. You'd say a volume. Okay, let's pretend it's 1 liter. Well, if I use 1 liter here, I said that my volume did not change, so I would put 1 liter on this side. If I said 1 mole on this side, but we said that the moles doubled, I would have to put 2 moles on this side. And the temperature, I put a value of, 300 Kelvin to use an easy number to work with. And they say that the temperature is tripled, so I would have to put 900 Kelvin on this side. And by the way, when they talk about the temperature and they say it's doubled and tripled, they always talk about the Kelvin temperature. This does not work with Celsius. So sorry. So you can assign values like this. As long as you're consistent with what the problem says, you will find the same answer in the end. So that's it for that. That's it for your general gas law, and stay tuned for your next episode.